So far we spoke about syntax of propositional logic, where we talked about some kind of conventions and then what kind of precedence, how you give precedence to the connectives etc., and how do we find out the major connective in a given formula and when it is considered to be sub formula etc. So let us quickly talk about semantics. Semantics, we talk about a formula which can be either true or false. From there are only two truth values that we have, since we are talking about bivalent logics. Only two values are permissible to us, either a sentence has to be true or false. So we, for semantics, what we require is a valuation function which takes up any propositional formula, the variables that occur in the propositional formula like p's, q's etc., and assign some kind of value. The only values that we can assign to the given propositional variables are either false or truth. So now, given the valuation function v, which assigns some kind of values to all the propositional variables, an interpretation function which is read like this v, which takes a formula and it generates it gives us some kind of value at f or t. For example, valuation of p and q, depending upon what value p and q has, it generates some kind of value for that one. If both p and q are false, then valuation of p and q is going to be false. So these are the minimal things that we need to note, that is valuation of a particular kind of thing. Contradiction is always false, all contradictions are obviously false. Evaluation function of valuation of p that is going to be true only when when p is considered to be true. For example, if you say New Delhi is the capital of India, of course that proposition is true. Suppose if you say something else, Mumbai is the capital of India, that sentence is false. In the same way, not A is true, especially when A is considered to be false. A and B, evaluation of A and B is going to be true if and only if both conjuncts have to be true. A and B have to be true. A or B is going to be true only when either one of these things are going to be true. And A implies B, this is what is considered to be the material implication. Classical logic follows material implication, and the definition of material implication is that A implies B is defined as not A or B, or it is not the case that A is true and B is false. So based on that, A implies B, evaluation of A implies B is true if and only if valuation of A is either false or B has to be true. So a propositional model, now we are talking about a model which consists of propositional symbols which belongs to some set of propositional variables, and we have some kind of validity relation which we write it as double turnstile. So there is a difference that we will be following, that is like this. So we make use of two symbols. So in the syntax we talk about this particular kind of symbol, single turnstile B. This means from A with some kind of axioms, together with A you are deducing B. So B is deduced from A. When I write A single turnstile B, it is we are trying to talk about something about proving something. So this is what a syntax is all about. When I write like this, A double turnstile B, this means under all interpretations where A is true, B also has to be true. And this symbol we discuss it in greater detail a little bit later. So this is also called as logical consequence or semantic consequence, or you can say that B is a logical consequence of A, or you can also talk about this thing in a different way, that A makes B true. The idea here is that if you take it as on the left hand side, these are premises and this is the conclusion. In any given valid argument, if the premises are true, the conclusion cannot be false. If you come across a situation where this A is true but B is false, then B is not considered to be a logical consequence of A. For example, if you have A implies B from that if you say not B. So under some particular kind of assignments or interpretations where the left hand side is true but the right hand side is going to be false, then this not B is not considered to be a logical consequence of A implies B. So now in this given model M, P belongs to P is a logical consequence of model, particularly when it belongs to M, and not A is true in a model M, particularly when A is not a consequence of M. A should not be there in your this thing. Now A and B is true in a model M when both are true, and A or B is going to be true when either one of these things are true. A implies B is true, and we just follow the definition of material implication, that is not A or B. That means not A means A is not a logical consequence in your given model, but B is a logical consequence of your given model. So there are some definitions that we need to note, and with this we will end this lecture. So that is, these are the important definitions that we need to note with respect to the semantic consequence or a logical consequence. So a formula A is considered to be valid with respect to a given model M, or you also call it as M satisfies A, if and only if A is a logical consequence of that particular kind of model M. When A is not a logical consequence of M, then A is considered to be refuted by M. Refuted by M means this M can make the formula A false. So just like A implies B, from that B follows. B is considered to be logical consequence of A implies B, whereas not B is not a logical consequence of A, and A implies B. And there is one more term that you will be coming across in this course, that is satisfiability. A formula, any given formula in the propositional logic, is said to be satisfiable if and only if there exists some kind of model M such that M makes the formula true, at least in one particular kind of interpretation. If A becomes true, then it is said to be satisfiable, and it is refutable if some model refutes this thing. Under some interpretations, if the formula A is going to be false, then it is said to be not satisfiable. And a formula is also considered to be valid. Why we are interested in validity is because all the validities are tautologies, and all the true statements are considered to be valid in propositional logic. A formula A is considered to be valid if and only if every model satisfies the given formula A, and a formula A is considered to be contradiction if and only if every model refutes given A. So these are the things which we discuss it in either in the truth table or in the one which we will be talking about in the next lecture. So that is semantic tableaux method. Using semantic tableaux method, we will be talking about all these things in greater detail. When do you say that two formulas are considered to be logically equivalent to each other? That is A if and only if B or A is equivalent to B. They exactly have the same models. That means if the truth table matches, then of course they are considered to be logically equivalent to each other. Not A or B or A implies B, they have the same kind of truth values. So obviously truth values matches, that is why they are considered to be logically equivalent. There is another term which you come across, which is called as compactness. Compactness is like this: a set of formulas in a given set of formulas like gamma is said to be satisfiable if and only if, even if you take the finite subset of such particular kind of set gamma, and they are also considered to be satisfiable. If that is the case, your that is considered to be compactness. So in the next lecture we will be talking about a particular method which we will be employing it in our course. So that is semantic tableaux method, with which you will be talking about these things, that this is considered to be a decision procedure method, with which you will come to know when a given formula is considered to be a tautology, or when two groups of statements are consistent to each other, or when something follows from something that is considered a logical consequence, or when two formulas are said to be logically equivalent to each other. We are still talking about the basic concepts of classical logic. All these things we make use of it when we discuss about advanced concepts in modal logic. So, in the next lecture we will be talking about the semantic tableaux method. Thank you.